Hi, thank you. Thank you so much. Okay, so thanks to everyone. Well, thanks to our last speaker and to all the useful discussion we've had there and the questions. So my name's Matt Palmer. I'm going to introduce this next panel session. So this is my first time at the Climate Robotics Summit. So thanks to the organisers for inviting me to chair this session. I work at the UK Met Office, but I'm part of a larger organisation which is called the UK National Climate Science Partnership. And that's a group of government labs which really a lot of the national capability for climate sits within those labs, the sort of long-term strategic national capability. And broadly speaking, that capability fits into the observational space, but also the modeling and prediction space. So both the sort of supercomputers and modeling capability, but also critically the observing capability that we have for the climate system and the Earth system more widely. And that's really the topic of this session, is really thinking about the advance of robotics and the role in Earth and ocean observation. So I'm very much a climate scientist. I've been involved in the IPCC assessment reports and things. So I come at this very much from a science question focus and a societal need focus. I'm really fascinated to hear about the developments in the various areas that we're going to hear from our panelists. So that's Enrico, Michal, Maarja, and Weifeng, and we'll hear from them shortly. I'm going to ask them each to introduce themselves briefly and give a couple of minutes on their area of research. Then we're going to move into a sort of a bit of Q&A from the panel. So I'll ask them a series of questions. And then what I hope we'll have time for is some audience participation. So there should be a chance for you audience members out there to post your questions into the chat, and we'll pick some of those up, and then we'll have some closing remarks from our panelists at the end before we move on. So I think that's all I wanted to say by introduction. I would love to invite our panelists now to each do about a couple of minutes on what their area of work is, and sort of talk about the developments briefly in those areas. So let's do it in the way it's written down on the slide here. So that'll be Enrico first, then Michal, then Maarja, and then Weifeng. Thank you very much. So over to you, Enrico.
Hi, everyone. Thanks so much for having me. I'm super excited to be here. So my name is Enrico Ajanic. I am a senior engineer at Meteomatics. Meteomatics is a weather intelligence company from Switzerland. And what we do is basically two things. So one thing is we develop a highly accurate, high resolution weather model. And on the other hand, we develop these drones, meteor drones that you can see here in the background, which are used to measure, well, basically to do atmospheric sounding of the lower boundary layer, lower atmosphere, up to 6 kilometers, so three and a half miles up, straight up. Yeah, so these drones, we use them. Those are not separate parts. So basically, we use the drone data and we also feed that into our weather model, together not only with the like satellite data and also the other weather models. And with this, we can improve the lower boundary forecasts. We've shown that we can forecast fog much better, like thunderstorms, local winds, and so forth. And so we do this. So last year alone, we flew about 6,000 flights with our drones. We have them. Right now, we have a network of about 11 meteor bases and drones in Switzerland. They're fixed locations, and we're currently building up 30 bases in all over Norway. And with that, we can then provide very, very good and very nice weather data to our customers.
Fantastic. Really interesting stuff. Okay, so let's move to our second panelist now, Michal. Hopefully I'm pronouncing your name correctly. Please, please correct me if needed.
Sorry, I forgot to unmute myself. Um, my name is Michal. I work on developing balloons at WindBorne Systems. So, WindBorne Systems is a company that does two things. One of the things we do is we have a um, long duration weather balloon that we maintain a constellation of. And then those balloons collect weather data from around the world that gets ingested into our ML powered weather model that then we use the forecast to, predict various things about the atmosphere. Uh, I can talk a lot more about the balloons because that's the area I work on, I'm excited on, and I did break the rules a bit because I edited the background and you can see one of our balloons here in my background. Um, yeah. Um, so to give a bit of background about how our balloons are different from other balloons, typically radiosondes they get launched and they go up collecting a single vertical profile of the atmosphere over a couple hours, and then they pop. The world launches over 1,000 of those every single day. Uh, our balloons are, I like to call them like weird robots in the sky, in that once they get launched, they stay in the air for possibly up to several months. Our current longest flight is over 6 months and counting. And while they're in the air, they go up and they go down, collecting profiles continuously. Currently, we have around 330 of them in the air um, at this moment. The goal of the company is to reach 10,000 aloft at any given time. That kind of gives the same density of observations um, across the entire world that are currently only observed in areas of Europe and North America. Um, yeah, thank you.
Great, thank you very much. Really interesting. So let's move to Maarja next. Thank you.
Hello, my name is Maarja, and I'm very glad to participate on this session about ocean and Earth, because my research is actually about neither of us, or it's actually about both of them. So I'm doing my research on an interfaces of the land and the water. And why is this important anyway? Because in robotics, we like to go very far and we like to be very high and we like to go very deep. But actually, there is also a very big challenge of going very, very close and going very, very shallow. And why is this so difficult? And why is this important? It's important because actually every ocean starts with a shore. And on every shore, there is an environment which is really not a land and which is not really ocean, but a mixture of both of them. And with this 1 minute left, I try to convince you why is this important to go there and why is a specific challenge for robotics. First of all, when you think about surf zones and very shallow water, so they're often with a very difficult, complex dynamics. And if it's with a complex dynamics, it means it's also very complex to control. Besides that, it's also very hard to get good data out of that because most of the sensors that we use in robots don't work in environments like that. For example, cameras in turbid waters and so on. And also, if the water is really shallow, then we also have a problem of so we can't go there with big vehicles. We have to make them some small, and when we make them small, and every engineer knows that service troubles begin with a miniaturization. Now with going a little bit further away from the water and into land, then you end up in an environment which is a mixture of a water and dry substance. Could be mud, wet sand, wet snow, sludge, something else like that, which is a completely different challenge because you're still kind of on the ground, but you don't have really proper ground reaction forces. The interaction with the environment is very complicated. And besides that, there is also a big engineering problem of corrosion and abrasion. So why should we do it anyway? Because those environments actually are quite abundant So everywhere, they could be like, as I said, shorelines, riverbanks, they could be swamps, bogs, lakes, but they also, for example, water treatment plants, and there are also sewer networks where you end up in an environment like that. And often these environments are biodiversity hotspots, so they are important from a point of view of climate research, but they're also places of very active human activity, so they are also important economically. So we have very little data from those environments, and when we have very little data from those environments, it's very hard to build models. If we have very hard to build models, then it's very hard to predict what's going to happen in places like that. And this is why my research is focusing on that. Thank you.
Brilliant. That's really fascinating. Thank you so much. Okay, so we'll move on to our last panelist, Weifeng.
Hello, everyone. So my name is Weifeng, but everybody calls me Gordon. So I'm here at Woods Hole Oceanographic Institution in Massachusetts, USA. And actually, at this moment, I'm actually at the sea. I'm calling in from a boat, from a ship, a research vessel. And I was worried about the internet, but so the ship operators confirmed that the internet should be fine. So indeed, so I'm really happy. And so I'm a senior scientist at Woods Hole, and I'm actually a physical oceanographer. Means that I study ocean currents and how the water moves over different oceanographic environment, from coral reefs in the tropics to continental shelves and to Antarctica or Arctic. So I have a bunch of different projects. Okay. I'm interested in the slide, the bottom part is actually shifted. It's okay. So I study ocean currents, but I also collaborate with a lot of other scientists to study how the water movement affect biology, chemistry, or for biology from coral reefs to plankton to apex predators like sharks, tuna, or even whales. And then also study how the water movement affect like ice. In terms for Antarctica will be how it affect the sea ice melt and also the ice shelf melt, or for the Arctic will be the sea ice melt. So I'm not an engineer or I'm not a robotist, and but I'm a user of data from a robot for underwater robots and or a lot of So I collaborate with engineers or technicians to develop. They give them the scientific question, and they develop underwater robots, as I'm showing here. On the top is a robot a colleague of mine called Yogi Girder is developing to sample coral reefs. And so traditionally, we just use human divers, but that's very inefficient. So we are pushing forward to scale up the effort using underwater robotics. And then on the bottom left, I guess, for Antarctica, we really want to know how much heat the ocean water is bringing to the cavity underneath the floating ice shelf, and then melt the ice shelf from below. And for that is a area that is really hard to make measurements, and very few measurements are available. So we are designing a complete new type of underwater robots, or we also call it mooring, but self-deploying, but it has to function as a robots as well, going to the environment and self-deploying, and then measure the water movement, the turbulence, and also how much heat that go directly into ice. So that's me. Thank you for having me.
You're welcome, Gordon. Thank you very much. So thanks to our panelists for that round of introductions. It's really great to hear about your various projects, and I guess the stuff around Gordon's talk really resonated with me a lot, because my research field is really in sea level rise and sea level rise projections in the Antarctica, and those ice interactions are critical to determine those future evolution in that environment. So important that we're able to make these observations. So I'm going to come to each of you probably in the same order that you presented originally. And I'd really love it if you could give us a bit of an insight of what you think some of the big, either technical or scientific challenges are within your field. So what are those really hard things to do that you found a way to solve or improve our knowledge? And And what has that meant? What sort of advances have we been able to make because of that? So just give us a sense of what either technological or scientific challenges do you feel your work has really been targeted at, and what has been the outcome of either addressing or making some progress? So let's go to Enrico first.
Yeah, so technological challenges. So in my case, again, so I'm developing these drones that we use for atmospheric soundings, and they only make sense if you can use them in the weather that you want to measure, or in the atmospheric conditions that you want to measure in. And in our case, that can be rain, that can be fog, that can be icing conditions, that can be strong wind, thermals, and so forth. And so in our case, we had to develop drones that can cope with all of this, and that can at the same time also do these soundings in a fast manner. And so we had to find technological solutions for these problems, and we have achieved this. And now really our drones, they can fly in really, really harsh conditions. And as I said, so with last year we had 6,000 flights in all kinds of weather, heat, snow, and we could show that it works, and that we can produce very good data. And this data then also leads locally to where we measure this data can lead to a very, very good forecast. Again, one thing was fog. We flew through fog layers, and we could show we could show that fog might remain for longer, or it might form even if temperatures were low, and it was actually a great hazard for us. Yeah, and I think that's one of the main challenges that we're trying to solve. Yeah.
Great.
And one challenge, of course, we've solved already compared to weather balloons, so we don't produce garbage. So our drones, they don't pop, they don't fall off the sky and then have to be picked up. The cool thing is we always go up, come down again, and we can recharge the battery. Yeah. And we can do it in a very regular manner. So we fly up every 20 minutes. Yeah.
Wow. Yeah, so I'm sort of thinking about the linkages between your work, which seems focused on the weather timescales, and wondering about the link to climate and maybe process kind of understanding and better being able to understand some of these smaller scale phenomena, I guess, and maybe start to take that learning into our computer modeling systems and other modeling systems for prediction. So just sort of trying to join the dots between some things. I guess the other thing that I sort of struck me a bit between, probably applies to all of you, is the harsh nature of the environments you have to operate in is always, I guess, a challenge for us. I'm an oceanographer by training, and that's can be a pretty harsh environment to work in. But I guess the atmosphere just as much, right? Like with strong winds and all kinds of challenges there, with low temperatures, etc. Brilliant. So thanks. So we'll move on to Michal. So the same question about either technological developments that you've achieved, or scientific questions that your technology is really sort of targeted at. It'd be great to hear your thoughts. Thank you.
Yeah, thank you very much. So I think on the technical side of challenges we're facing and working on solving are, well, I was going to talk about first communications, because one of the advantages of balloons over drones and other kind of like local weather stations is that they fly all over the world, including over oceans, over poles, and in places where there isn't other infrastructure. That means that getting live data back from those balloons is a big challenge. You really have to talk to a satellite up in the sky, and if your electronics is super low power, then that's a bit of a challenge. That's one of the problems we're working on solving. The other one is scaling. I know humanity has figured out how to make a lot of something, but this is something we as a company are figuring out as we go. We literally started as a student project who just built weather balloons for fun, and turns out there's a market for them, and then we started building more. And currently we're doubling our scale every 6 months. And making a lot of something is hard. Um, yeah. The other thing I kind of wanted to highlight is that after the balloons land, yes, they do land in random places, but because they're solar powered and communicate over satellite, we keep talking to them. So they become weather stations both on the ground and in the oceans. And one of the engineering challenges we're working on is our sensors, which are very optimized for, collecting atmospheric data. How can we make the same sensors also be effective at collecting high quality data from the surface of the oceans or, the surface of land? Um, so it's very fun because, yes, we do generate a bit of waste, like all weather balloons do. But our waste is useful waste. And it's kind of, turns out that we actually came up with this because after our balloons land, that our existing designs just kind of keep talking, and we're like, wow, we're getting data from like the surface of the ocean. Huh. We probably put in some effort into making sure that like after landing, they function as buoys. So yeah.
Yeah, it kind of strikes me that there's quite a high degree of complementarity potentially between the stuff you're talking about and Enrico's platform. Very different characteristics, observing in very different ways, and probably very highly complementary if you want a holistic view.
I mean,
So,
it's a very similar type of like build hardware, collect data, and then build weather models based on that data, with our data being, global and focused kind of in the, upper atmosphere. And I'm sure that Enrico's work is, from what I'm hearing, is, much more localized into places where your customers care about, and also focused perhaps on the lower, bits of the atmosphere. I actually had a question for Enrico. When measuring things about the air, you really like want to be measuring the air as it is if your vehicle wasn't there. And, balloons just kind of float there. They don't generate heat, they don't generate downdraft. How does your sensing system work on your drones to, not have the drone itself impact what you're measuring? Like, do you have like your sensors like long booms? Do you like
Very, very good question. But it's the same for you, right? With the weather sensors, you always need to make sure that the structure itself doesn't affect your readings, right? And in our case, I mean, we did a lot of campaigns to test and make sure that our platform does not affect it. And also with the wind measurements, I can say that we have a very smart algorithm that can calculate the wind direction and the wind speed. So it's not like I can't tell you too much about it, but yeah, it's so we verified it and made sure that it's proper. And you can also see that when we were part of the WMO campaign, and we compared our measurements there, and our measurements were very good. Yeah. But I would also one more point that I would like to add. So I think it's as you said, Matt, it's complementary. You need the balloons, you need the weather soundings with balloons to high altitudes. You also need the local weather. You need the satellite images. You need maybe even LiDAR data. So you need all of this data that you can then combine to a very good weather model, which is also what we're doing, right? So we have our weather model and we combine everything together, to get a good forecast.
Great. That's really fascinating for me. I spend most of my time thinking about the ocean, so the upper atmosphere. But I guess the other part I'm interested in is, I'm interested in the systems view and observing all parts of it. So this is a great session for me, really interesting. So let's go to Maarja now. Hopefully I might have pronounced your name slightly better than the first time around. Sorry about that. Let's go to you for the same question. So either technological or scientific challenge that your work is particularly kind of directed at. I guess you showed us a few kind of example applications, but maybe you might want to focus on one or two of those that you think are really important, where the technology is really sort of making strong advances in our knowledge or some, thank you.
Matt, you mentioned harsh environments, so I think this is something that's common for all of us, and it's also for a researcher. Some things that you're not used so much to think about, because there are actually not so many roboticists who do field robotics. So that actually means that you take your robots out and they actually work for a pretty long time, right? And this is not always happening in a research lab. So you're focusing on other things, which is like reliability, fault tolerance, durability, all this sort of things. And this is kind of a cross-cutting issue with if you go to environments like ICO. Another thing, sensors, you talked about sensors already, but in my case, I'm kind of in an environment where there is no information, there's very little information, and most of the sensors we use are failing. So it's often like, how do you get information from places where there's very little information, and how you use other sensor modalities to take out this information. And finally, when it comes to locomotion, as I mentioned already, these mixed environments are almost not addressed by robotics so far, I would say. And if I really would like to pose a really big scientific challenge to everybody, that would be, I would like to have a mobile robot without moving parts. Because like if you go into a sand or you go into a mud or somewhere, like guess what's going to happen, right? Yeah, exactly. So and it's not a joke in a way. I think it would need like a really, in one end, even a really great scientific breakthrough to come up with something totally different to work in environments like this. In my opinion, if you ask for a concrete example, very specifically challenging, I'm working in sewers. And why it's important, because we inspect at the moment about 1-2% of sewer network every year, which means that wherever you live in your city or town, it takes 50 to 100 years to inspect everything. And to have some things that moves in these environments, it's a very difficult challenge in terms of it's not water, it sometimes is water. It's not dry, it sometimes is dry. It's something, in between. And since there are sort of objects, there could be fat, and the worst thing ever is hair and textiles. As I said, I would like to have a robot without moving parts.
Okay, fantastic. Thank you very much. So before we move on to Gordon, I just wanted to invite the audience to maybe start thinking about some questions for our panelists here, and feel free to start putting those in the chat. And after we've heard from Gordon, we'll start going through some of those questions. And then toward the end of the session, I'll ask for one final intervention from our panelists before we close the session. So over to you, Gordon. Again, the same question, either a particular technological or scientific challenge that your work is really directed at.
Yeah, so again, I'm not an engineer, but I do communicate with a lot of engineers. So a lot of the challenges the previous speaker or previous panelists have mentioned also applies to underwater robotics. But the underwater robotics has even more challenges, like there's no GPS, right? There is no sonar panel you can use can get the energy. So the power consumption is a major issue, and underwater navigation. Especially if you're in the middle of the water column, you don't see surface, you don't see the bottom. What do you do, right? So a lot of smart engineers, a lot of my colleagues included, they're spending their whole career on those questions. And so that's technical challenges. And certainly they're making a lot of progress on that. And I can attest to that because I've seen some of the deployments of this underwater robots, and they're doing great. But another major challenge I see is the scaling. I think Michal mentioned earlier. And so right now we have a lot of fancy underwater gadgets, to measure coral reefs or ice or seafloor, but they're often designed or built for specific tasks of specific size or few size. And the ocean is vast. 71% of the Earth's surface covered with ocean, and with a lot of process going on from biology, chemistry, geology, and ocean is important to every one of us, but the connection to our everyday life is a lot of times indirect. We don't realize that most of the oxygen is actually generated in the ocean, or most of the CO2 actually goes into the ocean. But so there is not a big market. I think Michal mentioned there is a big market, so it's easier for them to scale up. But it's for the ocean, there is not a bigger market. So it's really hard for us. There's not a big investment in it. So it's really hard for us to scale. But there's a need. From our perspective, there is a need because we really need to understand what's going on in the ocean, so we can save the marine biodiversity, or we can get resources from the ocean. And so that is a major challenge. How to scale, the technology we develop for particular use or particular size to a larger scale.
Great, thank you very much. I mean, one thing maybe I'll ask the panelists to think about this before I start looking at the audience questions, but it'd be interesting to think about whether there are things that this group could learn from each other. I feel like I don't know how much crosstalk there is about from firms working in different kind of environments, but presumably some of the challenges are sort of have some similarities. So I'd be really interested to know whether there are fora for, I mean, maybe this meeting is one of those fora, or this conference is one of those fora, but the sort of learning, I guess, from different fields, slightly different fields or slightly different applications. So maybe have a think about that. But I can see there's at least one question in the Q&A tab. So I think for those of you, hopefully you guys know how this works, but hopefully you can get a hold of the Q&A. And I can see there's a question for Michal, which says, what are the environmental impacts of the balloons, especially when they pop? Are they made of eco-friendly materials? It's quite a long question. So I'll ask the last bit as well, and you can think about it. So the last bit is also, how do you decide where to launch them? And does this not affect air travel, bird flight paths, etc.? I'm intrigued by the balloons, but have no knowledge on them, hence my question. So there's a few different aspects to that, but Michal, please feel free to
So I'll
respond.
kind of
Thanks.
take the questions in order.
I think so. So the first one was, what is the environmental impacts of the balloons when they pop? That's the first question. Yeah.
So they do land in random areas of the world. And there's a couple of framings to this. The first one is that we are replacing traditional radiosondes, which already do this. They land in random places and typically don't get collected. Because our balloons are around 100x more efficient in data collection per balloon, by using our balloons instead of radiosondes, it's a waste reduction rather than a moving waste to zero. For kind of a sense of scale, we pay for plastic offsets for double the amount of plastic we put out into the environment. It was actually kind of hard to find a company that would work with us on this, because they were all like, oh, like your total amount of plastic being put out is so low that it doesn't qualify for like minimum quantities that compared to other businesses that work with them to pull plastic out of the oceans. And we're eventually able to find one that works with us and pulls out double the plastic we put out. We do also have a website for people who are radiosonde hunters. So these are people whose hobby it is to go out into the world and find balloons that have landed in places. And we made a little app for them where they can they see where all of them are, and they can also rank the difficulty of like, oh, I tried getting this one, but I didn't have the right tools to climb a tree. But like, if someone's adventurous, they can go get it. That's one thing. And then the last thing is, as endurance increases of these balloons, we do have a fair amount of control about where they land. This isn't like pinpoint accuracy, but this is like, will it land in this 10-mile square area or this 10-mile square area? And we're thinking as constellation scales, we could end of life them in a specific area. Not like, again, point collection point, but think about a giant field and someone on an ATV driving around and picking them up. As far as this affects, air travel, planes broadcast. We do coordinate with both the FAA, kind of on a global, and then via the FAA with other organizations on like a global aircraft avoidance, but also with local air traffic controllers for our specific launch sites. We have 15 launch sites around the world, and we're expanding that. And the locations of those are mostly based on a combination of logistics, winds, and where customers want denser data sooner. For example, we have a collaboration with the Gates Foundation to have a launch site in Kenya that supplies the entire sub-Saharan Africa region with data. Planes also broadcast their location over something called ADS-B. And we use that data from planes that actually broadcast to basically like, hey, we're here. Like, hey, I'm here traveling this way. And we use that data to make avoidance maneuvers to avoid planes.
Okay, great. Yeah, it sounds quite sophisticated. That's brilliant. So there's another question I can see in the chat. So this is for Maria this time, which is, what is the best robot you have tried so far in those challenging environments, and why was it the best?
Thank you for the question. Depends on environments. Some things that I was really fascinating myself was a screw-driven robots that basically, drills itself or screws through the mud. And we very seldom see robots like that because normally we don't work in environments like this. They have their downsides, but it's something which is quite original. And yes, that's basically like personally my favorites that we have built.
Okay, great. Thank you. So we've got about a little under 10 minutes left. So I think what I'm going to invite the panelists to do is sort of maybe gives one comment on, I'm interested in this idea of complementarity or the synergies between these different platforms or learnings from each other's sort of work. Is there anyone who'd like to offer a comment or a thought on where they see, opportunities there?
I was thinking about the presentation of Weifeng about self-deploying robots. And I worked in Arctics quite a lot as well. And again, it's kind of, if somebody does robotics, they don't think about deployment and retrieval. It's kind of, you just do. But actually, if you go to environments like that, this is becoming the most difficult things to do. I think you balloon guys would probably agree with me that sometimes like those procedures are not easy at all, right? And we haven't thought about it that this is a scientific problem somehow to solve. Self-deployment is nice, but self-recovery is even harder, I think. I'm speaking from my personal experience. We just got retrieved the sensors that I deployed in Svalbard 4 years ago. So
Great. That actually sort of links very nicely to what was going to be another question for you guys that you can maybe think about as we start to wrap up, which was along the lines of, and I can see there's another question in the chat, so I'm going to come to that in a second. But it was around, I guess I'd invite you to either sort of present a sort of provocative point of view that that may not be widely held, a sort of so-called hot take. But the other thing I was thinking about is which relates to the last panelist intervention, which was, what is the one area that you think we urgently need more progress? And again, it could be a scientific or a technological challenge, or or what is the next frontier sort of thing. So maybe have a think about that. And then before that, I've got a specific question from the audience for Gordon, which is, in your work in the Arctic, what do you view as the most valuable data to gather to resolve difficult features?
Yeah, so I think the question is probably targeted toward Antarctica instead of Arctic.
Yeah, I
Yeah.
think you're
right. For Antarctica, to me, one of the issues the whole society is facing is the sea level rise, and how fast the sea level is rising, or it's going to rise. We actually, you probably can look at ICC report. There is a huge spread there. Depends on scenario. Even at each scenario, there is a huge spread. We actually don't know. So all the cities on the coast of New York, Shanghai, or all the cities on the coast, they have to cope with it, and they for the next 50 or 20, 100 years. So how high they need to build a seawall for, or how much they need to raise, or to build a new building, how high they need to build a new building for, all those has a huge implication for the society. And so knowing this rate, getting more precise estimate or projection of the sea level rise rate, it's critical. And we don't know that because we don't know how much the Greenland and Antarctica ice sheet are melting. And so to know that, we need to know what exactly caused that, the sea level, the ice shelf melt, because ice shelf actually provide the protection of the ice sheet on the continent. So how much the ice sheet is moving, it's melting, and then basically means how much heat that brought into the cavity space underneath ice shelf. And there are very, very few measurements. I can probably put on one slide. That's the measurement of that. And very hard to get into. Remember, we're under several hundreds meters of the ice. It's not just the ice, a couple of meters, but several hundred meter ice. and then several hundred meter below, the pressure is huge, right? So to me, that's the major question for people thinking about climate change or sea level rise. So that's why we propose to build this type of mooring that will go into the cavity. Remember, that's also tens or even a couple 100 kilometers deep. Go in there and self-deploying and really make the measurements right at the ice-water interface, right on the bottom of the ice shelf. And that the turbulence that brought heat from the water to the ice happens over that centimeter or a few meters still. So we're talking about hundreds of meters below surface, but also a few meters. So we have to make, so that's, to me, it's a critical question. And we're trying to build a platform to measure that.
Yeah, that's great. I mean, that's so sea level projections, as I said earlier, is my sort of field, and I agree with you wholeheartedly. I think it's fascinating that these small scale local processes at such fine scales can be the determinants of such broad, large scale impacts, if you like, climate impacts. It's fascinating sort of, scale discrepancy, if you like. So I've had one more question come in from the chat, so I'm going to ask that. So that's targeted to Enrico. And the question says, you said we need both balloons and your drones for high atmosphere and near ground. What's the spatial resolution you're aiming for? One station per 100 kilometer squares, one per 10,000 kilometer squares? It would be useful to, would it be useful to have robots traveling between your stations so you also have data from between stations? So I guess there's something about some sense of what the sampling characteristics might look like. Any comments on that, Enrico? Thank you.
So it's a very good question. I mean, generally, this depends on many things. So let's say if you're in an area where there are a lot of mountains and the topography is very complex, then you would like to have more measurement points because it affects the local climate a lot, or the local weather a lot. On the other hand, the more stations you have, the more expensive it gets, right? You need to deploy them. You need and these stations also cost money. So what we do now, as I said, in Switzerland we have currently about 11 stations, and we gather quite good data from that. But this is something that we need to figure out with time, what a good station is, what also the good locations are. Now in Norway, for example, since Norway is much bigger, there we set up 30 stations in different areas, and this is then also something to see, something we have to see if the weather model improvement is sufficient or not. And maybe in some locations where you have very mountainous areas, maybe you need to add more stations there. Whereas if you have big plains, then you can have much less. So yeah. That's one thing. And then the other thing is also, if we look at Europe, for example, it would make more sense to place these stations or meteor drones in more of or what we need to consider there is how the weather really moves. And it usually moves from the west to the east, right? And since we feed that data into the weather models, it makes now, this is very general, but it would make more sense to place these stations further to the west, because then the data that we gather there would affect the forecast that we have for the places further east much more. And so this is also a consideration that needs to be done. Yeah,
Thank you very much. Question. Yeah, that was great. Okay. So we're really into the last minute. So I'm just going to invite any last quick 10-second, 20-second closing comments from any of our panelists. Feel free to go ahead. And I still think we should target that as the sort of real challenges or the next steps. Something forward looking where we think what's that next frontier. So invite any of you to give a quick intervention if you'd like to. I'll pause for a bit. Enrico?
Maybe I can just say something very, very quick. Everyone's talking right now about AI, and we need AI to improve the models and everything. That's great. But I think we should also focus on gathering the real data, real local data is also just as important, and we really need that to refine these models. So AI is nice, but the difficult and sometimes tedious and expensive way of gathering good data should not be underestimated, and I'm hopeful that it won't disappear in all this AI talk.
I totally I totally agree with you. I'm not really an AI expert, but obviously I guess we're getting accustomed to the new world we live in, but training data is key, and I think it emphasizes the obs more and more in a world where people are doing data-led modeling. You need the data, right? Otherwise that's the premise of this middle approach. So I'm going to draw this session to a close. So thanks to all my panelists. Really fascinating work. I hope you enjoyed it online. I believe there's going to be a 15-minute break now for people to go and have a stretch and get a coffee or whatever you want to do, and then it will commence again. The meeting will commence again in 15 minutes. So thanks for having me, to the organizers. Thanks to everyone, and hope to see you guys again another time. Thank you so much.